thank you to Brilliant for supporting PBS.
Just over 3 million years ago, a giant ground sloth wandering through a tropical forest did something that seemed unremarkable. It kept walking. But these particular steps were anything but ordinary, because this sloth was doing something almost no big mammals had done for millions of years. It was walking from South America to North America. The land it walked on, the Isthmus of Panama, had only recently emerged from beneath the ocean, connecting the two continents after a 20 million year separation. And suddenly, South American creatures, from terror birds to giant sloths, found themselves with an entire new continent to explore, while North America's gomphotheres and saber-toothed cats migrated south. On land, the isthmus kicked off possibly the greatest natural experiment in the history of life on Earth, the so-called Great American Biotic Interchange, or GABI. But in the water, this narrow strip of land did something completely different. It divided. The isthmus split the Atlantic and Pacific into two separate oceans, and that division would have a much bigger effect on the planet than the land connection ever did. Because this tiny strip of land probably changed ocean currents around the globe, transformed climate patterns, and even helped trigger an ice age. In the middle of the 19th century, a naturalist studying fish in Central America noticed something odd. Of the more than 150 species he observed off Panama's eastern and western coasts, over 1/3 seemed to be identical, so the oceans must have been connected at some point. Not long after, Alfred Russel Wallace, yes, the Wallace Line guy, noticed a pattern in American fossils that would later be recognized as evidence of the Great American Biotic Interchange. So scientists began to piece together that an isthmus had risen to connect the continents and close off that once flowing seaway. And over the next century, as plate tectonics came into focus, they started to figure out the general picture of how this happened. See, after South America broke away from Gondwana in the late Mesozoic era, it had been isolated for millions of years, giving rise to bizarre creatures like car-sized glyptodonts and those terror birds. Meanwhile, the Farallon Plate was slowly subducting beneath the Caribbean and South American plates, triggering volcanism that built a chain of islands, the Panama Arc. And over millions of years, that arc crept eastward, eventually colliding with South America and driving uplift that pushed some of the seafloor above sea level while also causing more volcanism that helped build land. Eventually, this combination of volcanic activity and tectonic collision pushed enough land up to form the isthmus, transforming the Panama Arc from an island chain into a land bridge. But scientists still hadn't figured out one thing. When did it finally become a complete bridge, one that sloths could just meander across? The first solid evidence came from seafloor cores in the 1970s, which revealed that groups of tiny marine organisms called foraminifera began diverging from each other around 3.5 million years ago. Then, throughout the 1980s and into the 90s, scientists looked at DNA from marine species on both sides of Panama. They used the fact that DNA accumulates changes over time at a known rate to compare how different the Atlantic and Pacific populations had become and estimate when the populations split. This method is often called the molecular clock, and these molecular clocks also pointed to around 3 million years ago. And the fossil record on land seemed to agree. There were tons of terrestrial vertebrates crossing between the continents at this time. So a mystery solved, right? The isthmus closed about 3 million years ago. The timeline made sense, explaining why the GABI happened when it did, and why the oceans changed when they did. For nearly 40 years, scientists accepted it. But then, in 2015, 2 studies dropped just days apart that completely contradicted this timeline. The first study compiled fossil records from hundreds of sites across both continents, looking for patterns that previous smaller studies might have missed. They discovered that some animals hadn't waited until 3 million years ago to cross. Instead, there was evidence of earlier pulses of migration at both 20 and 6 million years ago. And that same study found that the sea creatures backed up this timeline too. Taking a wider look at genetic analyses, they found that some marine life actually began evolving separately around the time of those pulses of migration, as if something was already disrupting the flow between the oceans. The land migrations and marine divergences challenged the idea that the terrestrial groups migrated and marine groups split about 3 million years ago. The second study turned to geology, specifically tiny crystals called zircons that form when volcanic rocks cool. Because here's the thing, you ready? Panama's rocks have a very distinctive signature. They're around 50 million years old, and they formed in a specific volcanic environment that gives them a unique chemical makeup. It's like a geological fingerprint that's only found in Panama. So when the researchers looked at 15 million year old river and shallow marine sediments in South America, they found something weird. Zircons with Panama's distinctive signature mixed in, which meant that rivers were already carrying Panama rock debris to South America 15 million years ago. And for rivers to be eroding Panama and flowing to South America, Panama had to be above water and connected by land. Both of these studies pointed to the idea that maybe the isthmus existed as early as 15 million years ago, if not earlier, way before anyone thought. But scientists now faced a puzzle. If the isthmus formed that long ago, why did most land animals wait millions of years to cross? Because it's clear that the vast majority of crossings happened much more recently. And how were marine species still mixing between oceans until 3 million years ago? The evidence pointed to two different timelines entirely, and both couldn't be right, unless scientists were asking the wrong questions. Many answering the question of when did the isthmus form required asking a more specific question. How exactly did the final closure happen? And the solution came from a surprising place, looking at a modern example of what ancient Panama might once have been like, the Indonesian archipelago. You see, between the Sunda continental shelf on the Asian side and the Sahul continental shelf on the Australian side sits a group of deep water islands called Wallacea. Yep, named after the same Wallace. Wallacea is also a volcanic arc that creates both a partial barrier and a partial connection between two regions. These Indonesian islands form a chain with gaps between them, affecting migration on water and land in interesting ways. Like we talked about in our Wallace Line episode, even narrow gaps between the islands, with strong ocean currents rushing through them, can prevent land animals from crossing. Gaps like the Wallace Line, for example, are enough to confine most creatures to their respective sides, despite being only about 30 kilometers across. And that's because powerful ocean currents can help create these invisible barriers. Yet, some creatures do make it across, at least occasionally, and marine life can still mix through the channels between islands. So by 2016, scientists realized, what would it mean if Panama didn't form all at once, but instead as a complex chain of islands first that slowly closed over millions of years? This would explain everything in the conflicting data. There could be early islands above water separated by deep channels that still allowed for some marine mixing, while strong currents held off most of the land crossings until the very end. Armed with this new model, scientists could finally piece together a more detailed picture of the closure, with a timeline to go with it. Most scientists now agree that 24 million years ago, the Panama Arc, riding on the Caribbean plate, first collided with South America underwater. At this point, the Atlantic and Pacific Oceans were still connected, with deep channels open between them. But by sometime between 15 and 9 million years ago, some islands had pushed above sea level, which is why there's evidence of rivers from those zircons. Deep channels, however, continued to separate them. Then, by around 9 million years ago, the deepest passages closed, and deep water critters became cut off, while shallow water creatures continued to move across. As more and more land emerged from beneath the sea and got closer together, some animals were able to island hop across, explaining those early migration pulses. And only around 3 million years ago did the isthmus appear to close completely, forming a continuous bridge that allowed sloths and many others to wander across freely. Now, it's important to note that this is still an active area of scientific debate. While most researchers agree with this model of the isthmus closing gradually over millions of years, they're still arguing about the exact timing of different stages. But this new model helps scientists develop more detailed hypotheses about what happened next, and why. Because while scientists had long suspected that the isthmus played a role in altering the global climate, this new timeline helped clarify that it was the final closure that had the biggest impact. You see, for millions of years, warm equatorial waters had flowed westward around the globe, including through the seaway between the Atlantic and Pacific. But suddenly, in geological terms at least, that path was blocked, forcing these warm waters to flow north instead. And one hypothesis suggests that this deflection strengthened what we now call the Gulf Stream. Caribbean waters became warmer and saltier, and crucially, all that warm water now flowed toward Greenland and the Arctic. Warmer water meant more evaporation, and more evaporation meant more water vapor in the atmosphere, vapor that atmospheric circulation was carrying toward the poles. For the first time in millions of years, northern latitudes saw enough snowfall that not all of it melted during the summers. And as the snow accumulated year after year, it compacted into ice. By 2.7 million years ago, major glaciation had begun in the northern hemisphere. The Ice Age had arrived. Now, the isthmus definitely wasn't the only factor at play here. Global ice ages are complicated, it turns out. For example, during the period that the isthmus was forming, CO2 levels were also declining, which played a role in the global cooling that had already begun. And because there are competing factors, scientists still debate how much of a role the isthmus played in intensifying those global changes. Some scientists have even argued that the isthmus actually played no role at all in triggering the Ice Age, pointing to models that fail to show this as a straightforward cause and effect. The fact that it's been so difficult to pin down the exact chronology of the closure means that it also has been really hard to establish causal connections that result from that closure. But while the scientific debate continues, many researchers agree that this narrow strip of land probably played a key role in fundamentally reorganizing Earth's climate. In fact, this tiny piece of land likely shaped the climate we have today. But this geological saga wasn't some sudden crash of continents that suddenly built the isthmus. Instead, it was a 12 million year process of gradual closure, islands rising, channels narrowing, and currents squeezing through ever smaller gaps. And when the isthmus finally closed completely, this small strip of land, barely more than 50 kilometers across at its narrowest, seems to have had cascading effects across Earth systems, managing to not only reorganize life on 2 continents, but also redirecting ocean currents and helping to trigger an ice age, reminding us that sometimes relatively small changes can leave big marks on the planet's history.
Thank you to Brilliant for supporting PBS. Brilliant is where you learn by doing, with thousands of interactive lessons in data analysis, math, programming, and AI. Brilliant helps build your critical thinking skills through problem solving, not memorizing. And if you're into mathematics, Brilliant's newly updated math courses are designed to help build your mathematical intuition while making you a better thinker and problem solver. You'll work your way up through interactive challenges that bring abstract concepts to life. Brilliant courses focus on useful, applicable math concepts with the goal of achieving personal and professional growth. To try everything Brilliant has to offer for free, visit brilliant.org/eons or click on the link in the description. If you go now, you'll also get 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant.
One group of North American animals that flourished in South America were the dogs. But their fascinating evolutionary story was overlooked by Charles Darwin during his famous voyage, which is dumb because his boat was literally named the Beagle. Learn more in our episode, Darwin Missed an Example of Evolution Right Under His Nose. Also thanks to this month's eontologists who help connect us.
Jake Hart, John Davison Ing, Addie, Carl Wolfel, Juan M., Jackie Scott Ralston, Andy and Eric Higgins, Raphael Hassa, Melanie Lamb Carnevale, and Steve.
Become an Eonite at patreon.com/eons, and you can get fun perks like access to exclusive polls and videos from the Eons team. And as always, thanks for joining me in the Andy and Eric Higgins studio. Subscribe at youtube.com/eons for more tectonic tales. I can cry on cue. Do you want me to cry? I'll do it.
I don't think that's relevant.
Just give me 45 seconds.
But can you uncry?
Yeah.
You're crying right now. Yeah.
Can I uncry?
Oh my gosh. Suck it back in. Suck it in? Yeah, no. I was in.
It's like a geological fingerprint that's only found in Panama. See, I could turn it on and turn it off just like that.
That's good. That's good.